Hello everyone. In the last lecture, when we started about our discussion about recurrence relation, we have seen that there are certain problems which are recurrent in nature, and we formulate the solutions of the problem by solving the sub-problems or sub-instances of it, which indeed you have seen in your programming as recursions. We have also seen how to generate such kind of a recursion and how to solve the very elementary first order such recursions, both linear and non-linear, homogeneous and non-homogeneous, and with variable and constant coefficients. In today's lecture, we are going to discuss about that those are only first order recurrence are not all. So we also get scenarios where the term of nth term is also not only dependent on the previous n-1th term, but also dependent on previous to previous terms. So we call such kind of recurrences as higher order recurrences, where the nth recurrent term is dependent on multiple previous recurrent terms as well. So we will see how we can formulate such recurrences and how we can solve those. So we start with second order linear homogeneous recurrence with constant coefficients. So we say a recurrence is second order if its nth term is dependent on not only the previous but also previous to previous terms. So in this second order term, obviously the C0 and C1 and C2 are constant. So we have constant coefficients. And it's linear because every term occurs in its linear manner. And it's homogeneous because there is no added function of n with it. So it's fn equal to 0. So it's a homogeneous function. Now C0 and C2 can never be equal to 0. Because if C2 equal to 0, then the nth term is only dependent on the previous term. So it then makes it into first order. If C0 is 0, then again n-1th term is dependent on n-2th term, not nth term is not present. So again it makes it as a first order. So these two has to be non-zero to make the generic form as second order. Since it's a second order recurrence, so every term depends on previous two terms. So we need a base two term conditions T0 and T1 for this. So let's say T0 equal to D0 and T1 equal to D1. When D1 and D0 all are constants. So to solve such kind of a recurrence relation, we might seek or guess a solution like C into x to the power n if I put in terms of Tn. It will give me a so if I put Tn equal to Cx to the power n, so this might be a potential solution for this. So to have this as a potential solution, we need to put it in terms of Tn and make it as 0 as well. So when we seek for such a solution where C and x are not equal to 0, so we could divide this by C into x to the power n-2 everywhere as C and x both are non-zero and get this simplest equational form. So where there are different roots of this equation, there are two roots of this equation since it's a quadratic equation. So the roots, if I supply it here in Cx to the power n, will give me a recurrent solution for the generic second order linear homogeneous recurrence. So to obtain the roots, it's a school book mathematics that we will follow. It's just the Sridharacharya's rule, minus C1 plus minus root over C1 square minus 4 C0 C2 by 2 C0 minus B plus minus root over B square minus 4AC by 2A. That's the rule. So there are two roots with plus here and minus here. So these are two roots, and let us assume that there are three possibilities can happen in this equation. One, that every root is distinct and real. There are two different roots which are complex and conjugate pairs, as we often see. And there are two roots which are same, equal and real. So we will analyze that one by one every condition and try to find out what is the generic solution to this second order recurrence relation. So first, two roots are non-equal, that is distinct and real. That means C1 square is greater than 4C0 C2 for having it real, not the complex one. Now, since I guessed a solution like this and I got two different roots, so both roots are linearly independent, so there could be the solutions that I assume will be A1 R1 to the power n is a solution of this equation, and A2 R2 to the power n is also a solution of this equation. And maintaining the linear independency of these two roots, we can say the overall solution I can formulate is a1 r1 to the power n plus a2 r2 to the power n. This combines as the total solution. So which gives me a1 into this root to the power n. So do not get afraid by the equation, because in practical scenario we will just compute a value here. So here it's a generic form, so it looks horrible. Here also the same root I taken here, where a1 and a2 are arbitrary constants. Now from this answer and my base condition, if I try to put n equal to 0, then the answer will give the value here I get as d0. And if I put n equal to 1, the value returned by here is d1. Now from that I have to determine, there are two equations, there are two unknown a1 and a2 I have to determine from there. And once I can determine that, my final solution will be obtained. So let us determine the constants. So if n equal to 0, then these two terms vanishes as to the power 0 is 1. So a1 plus a2 equal to t0 equal to d0. If n equal to 1, then what happens? Look at this one, that d1 equal to t1 equal to this. So if n equal to 1 happens, so a1 plus a2 into minus c1 by 2c0. And this term comes with a1 minus a2 into this, because n equal to 1, so all these terms remain as it is. So this is the answer. And finally, when I see this one, I know a1 plus a2 equal to d0, then a1 minus a2 will be just an algebraic simplification of this, will come as this. Now a1 plus a2 equal to d0 and a1 minus a2 equal to this quantity, easily you can know, you can add it, and by 2 is your a1 and subtract it by 2 is your a2. So once you get a1 and a2 and you know this is your equational form, then easily you can finally give your unique solution as this one. Looks horrible, but believe me, we will see examples where this one we will try to formulate and then solve and take a number. So this will not look such horrible. So it's just the generic way I am trying to solve when my roots are two reals, this second order equation, and where my recurrence format, the closed form of the recurrence for the nth term will be this one. This is the constant into something to the power, this term to the power n, the one root. And this is another constant that I obtained from the base condition, applying the base condition. And this is the other root to the power n. Some examples. Popular example you have seen is of Fibonacci number. So Fibonacci number says you that your n plus 2th term is equal to n plus 1 plus n and nth term. Here the constants are all ones. It's homogeneous because no additional function is involved. It is linear because every term is linear. So it's a second order linear homogeneous with constant coefficient. And I know my f0 is equal to 0 and f1 equal to 1. So I will first try to formulate my characteristics equations by substituting it with this one. So it will be x square minus x minus 1, because this term c and x are not equal to 0. So this term simplifies as this. And you know this has two distinct roots. So minus b plus minus root over b square minus 4 is c, blah blah blah. You get this one as one root and this one as another root. I call it alpha and beta. So then our final form that we have discussed, that it will be two linear independent roots with the form c into x to the power n. So c into root 1 to the power n plus c2 into root 2 to the power n. This gives me the final answer. And if you derive the constants with putting as f0, that is n equal to 0 as 0 equal to this one. So c1 will be equal to minus c2. And then if n equal to 1, you will get the value of c1 and c2 with those two equations. And eventually you will get c1 equal to 1 by root 5, c2 equal to minus c1, which is minus 1 by root 5. So we call the solution as in Binet form, that this form, if you try to put this answer together, so alpha beta is this one, two roots. So 1 by root 5, alpha to the power n minus beta to the power n, because my second c2 is just minus c1. So this is originated by a mathematician called Binet. So this form is a Binet form where alpha is your golden ratio. You might be knowing this term. So which alpha equal to 1 minus beta. So this is your golden ratio. And this is the closed form expression for your Fibonacci number of nth term. This looks very tricky, that how I am getting a constant term by having a real number to the power n. But believe me, if you go along with f2, f3, f4, you will get a constant term which is just the previous two term sum. Because We just assume a solution and have proven that solutions over it and try to find the roots which could replace the solution. That's it, what I have done. So this is a direct application of whatever we learned or the mechanism we learned to solve the second order recurrence relations. Another example. How many number of subsets are possible from an n-element set such that there are no consecutive elements chosen? So suppose you are given an n-element set x1 to xn. Now you need to choose elements from this set to form a subset such that if you choose x1 you cannot choose x2. If you choose x2 you can neither choose x1 nor you can choose x3. So consecutive elements you cannot choose. So let's say the number of ways possible is an and we try to generate a recurrence for this. What will be my a0? Because a0 means that you have no elements in the set. So therefore there is only one subset possible, that is null set, and that null set doesn't contain any element which are consecutive, so there is only one possibility. If n equal to 1, you have one element in the set, either you choose this or you don't choose this, there is no option of consecutive choice, so your answer is 2, there are two ways to choose it. So these two are my base condition, let's say. Now how do I form the recurrence? Let us try to find that I have chosen n-1 term. I have chosen subsets from n-1 elements of S. Now what about the nth element? If I choose the nth element, so let's say that my n greater than true and my set, I have just, here I have mentioned x1, x2, so this will also be x1, x2 up to n, there are n elements, let's say. And if I choose my nth element in my subset, then I cannot choose n-1th element. So all the subsets that I can form with n-2 elements and choosing n elements is the answer. So this may be counted in an-2 ways. That is all subsets n-2 and every subset I just put a nth element there. The other option could be that I do not choose n, then all possible subsets in an-1 way, because I am now free to choose everything with n-1 as well. So the nth element I am not putting it. So this is the way we can count it in an-1. So all this, so the number of subsets that we can choose in that is an-2 ways, and the number of subsets that we can choose that is in an-1 ways, all of this formulates my final an. So that's why what we will see finally is the fact that an equal to an-1 plus an-2. But remember here a0 equal to 1, a1 equal to 2, which is, in case of Fibonacci, we have just 1 shifted by 1. So, if you solve it, it is just a Fibonacci number, as you can see, but your an equal to fn plus 2. So, your a0 is basically f2, because your f2 is equal to 0 plus 1 equal to 1, f3 equal to 1 plus 1 equal to 2. So, you can see a0 equal to f2, a1 equal to f3. So, this form is same as the Fibonacci number that you have derived, or the closed form for Fibonacci expression that you have derived. Only the point is that here your recurrence an is equal to the n plus 2th Fibonacci number. So the formula answer will be this. If you forget about the Fibonacci and map it with even with Fibonacci, just do by characteristic equation, solve the constants using the base condition, you will get exactly this one. But analogy wise, we can say that this is n plus 2th Fibonacci number. Another example, how many number of binary strings can you have which do not have consecutive number of zeros? So 1001 is not a valid binary string because it has a consecutive number of zeros, but 1010 is a valid. So I want to count all valid such strings where there are no zeros occurring together or in consecutive positions. Let's say for generating the recurrence, I assume Bn is the number of such binary strings of length n where no consecutive zeros occur. And for the nomenclature wise, we use Bn in the superscript as bracket 0 to count all such string ending with 0, and Bn superscript 1 to count all such string ending with 1. So Bn is total string which do not have any consecutive 0. Bn 0 is such kind of a string not having consecutive 0 but ending with 0. Bn1 is such kind of a string not having consecutive 0 but ending with 1. So you can see that Bn is nothing but Bn0 plus Bn1. because I am thinking of those strings ending with 0 and ending with 1 is my total set. But why this is required? Because if you try to figure out that what will be my Bn, see, if your n minus 1 number of string ends with 0, then the string that you can form in Bn must have to append an 1 to it. Because if you append an 0 with a string ending with 0, n minus 1 strings ending with 0, then it is a violation of consecutive 0 present. Whereas, if there are strings which are ending with 1 in your n minus 1 length, then to form from that n minus 1 length an n length string, you can obviously append both 0s and 1s. It will not violate the consecutive 0 set. So this governs the recurrence, that my n string is, if I end with 1, the n minus 1 string, I can append a 0 as well as I can append an 1. So there are the number of ways in which I can formulate no consecutive 0 constructed strings ending with 1 into 2 will be contributing to Bn. Whereas the number of strings having no consecutive 0 in n minus 1 length ending with 0, only it can place a 1 to that to form it. So every string contributes once. So Bn minus 1 ending with 0 string contributes once. So this is my recurrence. Now if you break that recurrence, this 2 into 2 pluses of Bn minus 1 ending with 1. So this will be Bn minus 1 ending with 1 plus Bn minus 1 ending with 0, which gives you Bn minus 1. And the remaining Bn minus 1 ending with 1 remains. So what is the number Bn minus 1 ending with 1? It is exactly the same number as the number of strings ending with anything, or exactly the number of the strings that with the n minus 2 length strings that are ending with 0. Why? Because the n minus 2 length string that are ending with 0 must append with 1 to form an n minus 1 string ending with 1. Right? So therefore, we can say that this is nothing but Bn minus 2 as well. So this count is same as counting as n minus 2 number of strings. Because if the n minus 2, let me give you a different analogy why these two are same. Because let's say your n minus 2 string ends with 0, you can append an 1 and get it. Your n minus 2 ends with 1, you can also append an 1 and with get it. So appending an 1 with any of the string of Bn minus 2 will result you this string. So therefore the counts of both of them are the same. So that's why Bn finally gets again a Fibonacci kind of a recurrence while n greater than equal to 3. Here you see B1 equal to 2, B2 equal to 3, which is again I can sense that it is n plus 2th Fibonacci number. But if you want to solve it, you just go by characteristics equations and all these constant terms to eliminate the constant a1 and a2 in a1 r to the power n plus a2 r to the power n formulation. So you will get exactly this one. So see, we just have different variations of problems where we could use the same Fibonacci number of constructs or the characteristics equations of the second order to solve those. Let us try to see another example. How many ways you can tile a 2 cross n chessboard with dominoes? 2 cross n chessboard means you have 2 rows and n columns. N is positive number. Therefore, we see that this is my chessboard and these are 2 dominoes that was given to me, 2 cross 1 and 1 cross 2. Now to tile it, see that I can place this domino in this fashion and the number of ways I can tile the rest is my answer. So the rest can be tiled in Tn minus 1 way, given that Tn is the number of ways to tile n length chessboard of width 2. And in another manner, we can just place horizontally 2 tiles and the remaining number of ways we can do it is my answer. So it is Tn minus 2. So these two types of tiling gives me a recurrence flavor that the number of ways I can tile Tn minus 1 with the first cell occupied like this, and the number of ways I can tile Tn minus 2 with the first two cells occupied horizontally with 1 cross 2 tiles. So gives me my answer. So again, if you are tempted to think, you will see that this is again a Fibonacci number, and it's just Fn plus 1. You see that if it will be Fn plus 1 because T1 equal to 1, which is our F2, T2 equal to 2, which is our F3, and so on. But you can independently solve it using characteristic equations and this. So I will just urge you to solve any one of these numbers which is also a Fibonacci number by yourself, so that you get a flavor of how to eliminate the constants and how to determine the characteristics equations, and the roots can formulate you to the solution. A new example. Suppose I am given 10 digit symbols and 4 binary operations over those symbols. I want to compute all possible legal arithmetic expressions without parentheses. That means arithmetic expressions with the binary symbols are legal if it is the operator is placed in between two digits, right? 2 into 3, 4 by 2, 9 minus 4. These are all legal expressions. So I am given a length n expressions. So 1 plus 3 minus 4 into 9 by 2, like that, where I will evaluate from left to right and also using the division first, then multiplication, then addition, then subtraction, this rule. But I have to find out how many such legal arithmetic expressions with n symbols can be possible. To look into this problem, let's say En is the number of such expressions possible. So let's say 0 into 1 plus 2, this is an expression. 1 itself is an expression which is legal because it's a digit. 99 is an expression which is legal, it's a digit. 999 is an expression which is legal. 999 into 2 is an expression. So you can see it in two ways, that if my last position of the expression in this n symbols must end with a digit, because you cannot end with a symbol, because have you seen an expression which is legal ends with plus, minus or star? It never, because it should be bounded with two digits at both of its ends. So its end point should be a digit. So if the last symbol is a digit symbol, then two ways can be possible in its preceding symbol. One way is that the preceding symbol is also a digit, maybe 99, 23, like that. Another way that the preceding symbol must be an operator. So let us try to count. So two ways to construct. If the last symbol is digit and the previous one is also a digit, then I have 10 as the last symbol, and the previous one is a digit is my recurrence n minus 1 expression ending with a digit, because I always assume that it will end with a digit. So 10 such possibilities of ending with a digit can happen, 0 to 9, and then the remaining n minus 1 could be again a valid expression, right? Even if it is ending with 99, I took 9 out, and the remaining 9 part of my 99 number, I take it with the others to form the recurrence. However, if the last symbol is a digit, before that we have an operator, then how many such possibilities would be possible? 39, because plus 0 plus 1 plus 2 plus 3 up to plus 9, this is 10. Minus similarly up to 10. 0 to 9 is 10 times, 10 number of those. Star 0, star 1, star 2, star 3, that is 10 in number. But by 0 is not possible, so there are 9 options for by with ending with a digit. So therefore my total recurrence is 10 En minus 1. This is 39 En minus 2 because 10 in each and 9 for the division. And the rest I recur with n minus 2 length string. So this is 10 into En minus 1 plus 39 into En minus 2. This is again second order, linear, homogeneous, constant, coefficient recurrence. What is your E1? That is with single symbol. What you can do? You can only have 0 to 9 digits. What is your E2? With two symbols. See now, you cannot place any operator if I only restrict with two symbol legal expressions. So there will be 100 of them. It is 00 up to 99. From 3 symbols, you have an options to put an operator inside it, but up to 2 symbols, there will be only digits. So this will imply my E0, that is with 0 symbols, I have no expression at all. And if you try to see here why it happens, you put E1, E2 equal to 100, E1 equal to 10, equal to plus 39 E0, so E0 will come as 0. So with this, let us go back to our previous constructs of solution, that we will consider the characteristic equation as x square minus 10x minus 39 equal to 0. Form give us these two roots and a constant, then finally giving the initial conditions and trying to solve for the constants will give me the constants as 5 by 3 root 6 and minus 5 by 3 root 6. So this will be my final answer. You put n equal to 1, you will get this. You put n equal to 2, you will get this. So interestingly, again this is also kind of a Fibonacci number type of a form, which for different value of n gives me a digit or an integer value, though it's a rational number. So we move forward with another example. How many n length words containing 3 letters only? So I will form n length words with these 3 letters that can be transmitted where no word are having 2 consecutive A's. So how we recurrently try to think about this? Let's say my first alphabet or letter in the n length word is A. Then obviously it should not have 2 occurrences of A. So if the first n length word letter is A, then the second letter should either be B or C. So if I put A followed by B and if I put A followed by C, then the n minus 2 length word Wn minus 2 gives me the way or the recur me and gives me a solution for those n minus 2 symbols possible. N minus 2 number of such n minus 2 length words possible. So for each of them there is Wn minus 2. And now if my first letter is not A but B or C, then what will happen? Then the number of words is possible, since A consecutive 2 cannot be is prevented. So B and C in the first position. So n minus 1 position will again recursively, this will be my answer. So see that Wn can be contributed by putting the first letter as A, following letter as B or C. That is 2 times Wn minus 2 count contributes to Wn. And also putting the first letter as B or C, that is 2 times the count of Wn minus 1 contributes to Wn. Hence the recurrence is like this. So Wn equal to 2Wn minus 1 plus 2Wn minus 2. With my W0, that is 0 length word, how many words of length 0 is possible? 1, that is the null word. I do not send anything, that is a word, null word. And how many words of 1 length possible? So there is no chance of consecutive A's happening. So it is A or B or C once I send. That's 3 number of words. These are my base condition. Characteristic equation is x square minus 2x minus 2 equal to 0, which gives you these 2 roots. And again you solve for the constants. So your solution, your exact solution will be C1 R1 to the power n plus C2 R2 to the power n. And C1 and C2 can be solved by putting n equal to 0 and n equal to 1 with these values as I have shown in the initial slides, and your solution will give you this answer. So this is the closed form for n length words possible having no 2 consecutive A's present in it. This is a very interesting example. So you have also seen these examples in your counting when you different ways you count and proven the number of palindromic summands. So palindromic summands are the way you can write the summands of a integer such that both way is if you traverse from both directions, the summands look the same. Suppose I write 4 is 1 plus 1 plus 1 plus 1 or 2 plus 2. But 1 plus 2 is not a palindromic summand, because in the right side to left side, if I read, it becomes 2 plus 1 plus 1. But 1 plus 2 plus 1 is a palindromic summand for 4, because right side and left side both gives me 1 plus 2 plus 1. So how many such possibilities? See, Pn is the number of such palindromic summand. So there are two ways to construct it. That consider this example. From 3 to 5, how do we construct? We can add 1 to both ends. So that is, both ends of 3 is just 3. So we add 1 and 1 here, it becomes 5. Palindromic summand for 3 can be done in this way. So I can add both ends as 1. So it will be 2 plus 1 plus 2 is this option. Or I could append both ends as 1 to make it 5. See, we are trying to formulate a recurrence. Therefore, for a number, we are trying to find another number just prior to it and use its number of count to deduce the recurrence relation for that number. That is why, if this is the possible number of ways we could express a number minus 2, that is or an odd number, the previous odd number, we just do it in 2 times the number of ways it has been expressed. Either by adding in both ends 1 or by appending plus 1 to both ends. That is 3 plus 1 left end plus 1 right end. 3 ones together plus 1 right end plus 1 left end. So 2 into all the possibilities of the previous odd number gives me the new number of palindromic summands for this odd number. Same happens for the even number as well. So this gives me that whatever be your number of palindromic summands you are computing for n is the number of palindromic summands for n minus 2 into 2, which is our recurrence. That is, Pn equal to 2 into Pn minus 2, where your P1 equal to 1 and P2 equal to 2. Why? Because if your number is 1, there is only one way to express it. If your number is 2, then there are 2 ways to express, that is the number 2 itself and 1 plus 1. So these are my base cases. Now if I try to solve it again, I go by so the characteristics equation is here. You see, your x square minus 2 is equal to 0. So x equal to root 2 or minus root 2. So solve for the constants and all, you will get this. Now the question is that for any n, I get this as my answer. So if I have to bound the count, that how many number of such possibilities are there for odd n? You see that for 3 it is 2, for 5 it is 4, and we go by that way. So it is 2 to the power of the previous odd, right? So we go by this way, that when n is even, my number is 2 to the power n by 2, and when n is odd, this is. So this will result me these two formula. How? You can have a simple observation for the even, n equal to 2k, you just put it here. In this formula, if you put it n equal to 2k, you will get it will be 2 to the power k. That means n by 2. What if you put it 2k minus 1, that is an odd number, you will get this formula as 2 to the power k minus 1. What is my k minus 1? See, your n equal to 2k minus 1. So your k minus 1 is just the floor of n by 2. Because it is n by 2 minus, it is n by, so you put it k minus 1 here. So it will be n by 2 minus half. So it is just floor of n by 2 to the power n by 2. So this is a closed form formula for even and odd. But however, the recurrence relation we solved it gives us this one. So for every n, this relation will give you the answer. See here, how the number of count is dependent not only with the previous one, but also with the previous to previous term. That's why it's a second order recurrence. So one lesson here is that it may not be dependent on the previous, but dependent on previous to previous. Also qualify it for the second order. As in the generic format, we have shown that C1 and C2 not equal to, C0 and C2 not equal to 0, C1 can be 0. There is a very interesting example. We will, the set of examples for this kind of recurrence, we will end it by this. So how many number of divisions in Euclidean GCD computation process we do? So Euclidean GCD says that how we compute the GCD. So by Euclidean way, that given two number A and B, we try to divide A by B, take the remainder, and with that remainder, again divide B with that remainder, take the remainder, divide the first remainder with the second remainder we got, and so on. We go on processing it until we found that a remainder is divisible by the last remainder. So mathematically, we start with R0 equal to A, R1 equal to B. So first A equal to Q into B plus R0, R2. So this is your first time remainder when you divide this by this. So I want to compute till the end how many number of divisions are possible. And I want to bound that number. So your formula will be R0 equal to Q1 R1 plus R2. So this is your first division, where obviously R2 must be less than R1, and it's a remainder. It is not 0, because otherwise I could have said that GCD is R1 itself, because it is directly dividing R0. So R2 must be greater than 0 and R1 must be greater than R2, because otherwise I could have Q1 plus 1, another result. I can increment the result by 1 to get it. So this relation is valid, and my Q1 should be greater than equal to 1, because it is at least once I can divide. So again, I take this remainder to divide my R1. So my R1 will be Q2 into R2 plus R3 with the same relation holds, and so on for the next one, and proceed this way. So what does eventually it goes to, that when you get the remainder Rn while dividing Rn minus 2 with Rn minus 1, and if your solution is Rn, then Rn must divide Rn minus 1. So divide means that your Qn must be greater than equal to 2. Because if it is 1, then Rn minus 1 is itself equal to Rn. Then here in this step, I would have got the solution. So wherever I get the final solution, that step, I do not have any remainder anymore, and my Qn must be greater than equal to 2. And obviously Rn must be less than Rn minus 1 due to this relation here. So this is just how do we compute the Euclidean GCD. As you all know, this is a school book method. I just mathematically formulate and present to you, so that I could understand the bounds in the number of divisions. So you can easily see there are n divisions we are doing till the end, because here with the first division, second division, third division, this is n minus 1th division, and this is nth division, to find out that indeed Rn is my answer. So now let us try to see what is n, because that is the number of divisions which we are trying to compute. What is n? What is the formula to get n? So Rn is obviously greater than 0. It's a remainder which is greater than 0, obviously. So this remainder suggests me that Rn greater than 0 means Rn greater than equal to 1, which is the second Fibonacci number. So Rn greater than equal to second Fibonacci number. Now you see Qn is the last quotient, so it is greater than equal to 2, as I have already predicted. And my Rn I have proven to be greater than equal to second Fibonacci number. So just moving one step backward, what I could say with Rn minus 1? Rn minus 1 is equal to Qn Rn. Qn is greater than equal to 2. Rn is greater than equal to F2. So it is 2 into F2, which is 2 into 1 equal to 2, which is now F3. See, Rn minus 1, I get it F3. So what I am trying to do here, I am trying to bound every Ri's with respect to a Fibonacci number. And I am successful till this point. Let us see the next point. Qn minus 1 is greater than 1, this step. Rn minus 1 is greater than F3, Rn minus 2 is greater than F2. See, everything is greater than 1. So this will become 1 into F2 plus F3 will become F4. So Rn minus 2 will greater than F4. The next step will become 1 into F4 plus F5, which will be F4 plus F5, F3 plus F4. which will be equal to F5. Proceeding in this way till the beginning, we found that R2 must be greater than equal to Fn minus 1 plus Fn minus 2 is Fn, and R1, which is indeed our B that we started off with, is greater than equal to Fn plus 1. I want a bound for n, yet I have not reached. I have shown that if there are n number of divisions, then the number that I am started off with A and B, that B number, which is obviously less than A, is at least Fn plus 1. Now there is a very interesting property of Fibonacci number which says Fn equal to the golden ratio to the power n minus 2, that is this to the power n minus 2. I am leaving the proof for you because this is pretty straightforward by mathematical induction. You can easily go with mathematical induction and prove this formula. Very simple. So let us for the time being assume that this is indeed true, and you will get it if you do it in a pen and paper. So Fn equal to alpha to the power n minus 2, alpha is my golden ratio. Now I will try to substitute it here. What do I see? That Bn greater than equal to Fn plus 1, this is just by the mathematical relationships of Euclidean division I formulated, which is greater than alpha to the power n minus 1, which is this. And I know that A greater than equal to B greater than equal to 2 obviously, so this is where A and B I started off with. And it needs n divisions, I need to bound n. So I will see now this greater than equal to this gives me a chance to have n something. I mean, if I take a log and do some mathematical jugglery, I will get a bound for n. What is that bound? So B is alpha to the power n minus 1 to get it simplified. Log B base 10 is n minus 1 log this, which is greater than equal to n minus 1 by 5, because if you say log of this, you will get almost 0.21, which is greater than 1 by 5. So it is greater than n minus 1 by 5. What is it? Results that your log B is greater than n minus 1 by 5, and let's say B is a decimal number of k digits. So therefore B must be greater than 10 to the power k and less than 10 to the power k and greater than 10 to the power k minus 1. It's a k digit number in decimal. So this must happen. You can take any k and just try to verify. Now B less than 10 to the power k means k greater than 10 log B, and I have seen log B greater than n minus 1 by 5, which means k greater than n minus 1 by 5 means n less than 5k plus 1. What does it suggest? What is my k? It's the number of digits in B. So therefore, n less than 5k plus 1 means n less than equal to 5k, right? So this gives us the theorem that we are trying to solve in terms of this example, that number of divisions performed with two numbers taking as GCD is for at most 5 times the number of decimal digits in B. So when we say at most 5 times means n less than equal to 5k that we have just formulated from these expressions. And moreover, we can also see that n, if you take this k is log 10 base B, because B is of k digit. So n less than 1 plus 5 log 10 base B. And if you see that B greater than equal to 2, which means log 10 base B greater than equal to log 10 base 2. So therefore 4 log 10 base B greater than equal to log 10 base 4 log 10 base 2, which is log 10 base 2 to the power 4, which is more than 1. So if I can replace it here with 4 log 10B, so this gets n less than equal to 9 log 10B. So I can say order of log 10 base B. So n is of the order of the number of digits present in B. So that's what the number of divisions performed in Euclidean GCD. We can see that the number of divisions performed in Euclidean GCD is of the order of the number of digits present in B. So we just extend this, that if we have seen that the roots in the characteristics equations gives me the real and distinct. What if it's a complex conjugate pair? So the same thing we will do, it's a conjugate pair. So we will try to simplify it using r theta planes. So this is a simple math. You can easily know that it's r cos theta plus I sin theta and so on for xy, where r is root over x square plus y square and theta is tan inverse y by x. And if you solve it the same way, remember it's two different roots, only the complex conjugate pairs. Instead of real, we got a complex number here. So we can do it this way. And if you use De Moivre's theorem, then this is r theta coordinate wise. If you put it here, this will be the same as this, where your A1 plus A2 will be B1 to make it simplified more, and A1 minus A2 into I will be your B2 to eliminate I from here and put it in the constants and make it this way. So it's a simple jugglery of two different answer roots which is conjugate complex pair. So I am using De Moivre's, and then just the same way we determine the constant by putting n equal to 0. So this is T0, which is D0 given to us. And if you put n equal to 0, what it means, it is cos 0 plus sin 0. So B1 cos 0 plus B2 sin 0 is B1. N0 gives this part as 1. So just D0 equal to B1. And your B2 is nothing but, if you try to compute your B2 using the formula here by putting T1 equal to D1. So this comes as B1x plus B2y. This is a very simple algebraic manipulations that you can do in pen and paper. So your B2 becomes D1 minus D0x, because my B1 is D0, by y. Just putting it all together in this format, I get this as my expression, where there is no I, remember, though the roots are complex. So even if you have complex conjugate pair of roots, we can have a recurrence relation closed form which must not contain I, but this complex conjugate pair of roots, when we determine constant and go along with our dimension or the modulus and everything and formulate it, we will get this as the closed form. Let us take an example, because this looks scary when we do for the generalized case. Example wise, this becomes much more simplified. So let us find the value of the determinant of n cross n, this determinant, and where this is first 2 columns are B, 3 columns are B, and these 3 columns are shifted and so on till here, and again I end up with 2 B's. So what is the base condition? So first is, if you have 1 cross 1, you have only 1 B, the first one, which is B. If you have 2 cross 2, you only have 4 B's here, which is 0. If you have 3 cross 3, 2B followed by 3B, and the end with 2B. If you compute it, it will be minus B cube. This is your recurrence initial conditions. And how do we proceed? Now what will be my generic recurrence? I could have B into this part. What is this part? If you remove first row and first column, B into this part is just nothing but Dn minus 1, because it is n minus 1 cross n minus 1, and it looks like the same as Dn. So B into Dn minus 1 minus B square. If you take B and this B, others are everything 0. So B square into Dn minus 2 part. See, again Dn minus 2 looks like just like Dn. So it's a simplified recurrence. If you unfold it with one layer, you will get this. Dn equal to B Dn minus 1 minus B into B Dn minus 2. So B Dn minus this part, the right side without first row, first column, minus B square, this 2B square with this part, with this 2 part. So here you see that the characteristics equations become x square minus bx plus b square equal to 0, and you will see there are complex roots. So the solution would become a1 into that to the power n, and the a2 into this conjugate pair to the power n, and b to the power n is there in the roots, so you get it. So we put it in the r theta coordinate as this way, where you try to estimate b1 and b2, and indeed when you estimate b1 and b2, you will get your b1 and b2 as 1 and 1 by root 3. So this is just, if you follow it by yourself, you will get it. So this is just 1 and 1 by root 3. So finally, you get your final solution as b to the power n into cos n pi by 3 plus 1 by root 3 sin n pi by 3, that is 1 here in the constant and 1 by root 3 here in the constant. And if you give 0, you will get b. You give 1, you will get 0. You try to check it here. So, but for n equal to 1 and all. So this is how we use if there are two different roots, if it is complex, we just use this kind of arithmetical jugglery to find out our final solution. The last kind of root that is possible is nothing but two roots are equal. So see, if two roots are complex, then it could not be equal. It should be a conjugate pair. If two roots are real is another option, and two roots are equal is the last option. So two roots are equal means your C1 square equal to 4 C0 C2. That's why through your Sridharacharya's root solution equation, you get minus C1 by 2 C0 only. The other part vanishes. So this condition must hold when this characteristics equation gives you two equal roots. So when you try to solve it, now you get a problem because your two roots are now linearly dependent. To make an independent solution from it, you have to take this as a1 r to the power n, but you cannot take directly a2 r to the power n again, because then a1 plus a2 into r to the power n is just these two are linearly dependent. To make it independent, I just introduce a function of n into r to the power n, which is not a constant. How does it help? Let us see. That when you say that this is a solution, so first I try to put this solution in my original equation and see what does Gn can contain. So when I put this in my original equation, I get C0 Gn into this is the root to the power n. So I put this one in the original form. C1 into Gn minus 1 into this to the power n minus 1, C2 into Gn minus 2, this to the power n minus 2 equal to 0. This is from my original equation, putting this as an answer. So I get here Gn minus this as simplified, because you can always exchange C1 square with 4 C0 C2, and you know that C0, C1 and C2 are all not equal to 0. So you can cancel out if they are common. So for example, you can see that C1 to the power n minus 2 is common for all. You can cancel out because your C1 is not equal to 0. Why? Because C0 and C2 are not equal to 0 as per by definition of second order recurrence. C1 square is equal to multiplication of non-zero quantities, must be C1, must not be 0. So that's why when you simplify this by your hand, you will get that Gn equal to minus this one, 2Gn minus 1 plus Gn minus 2 equal to 0. This gives me that a solution that if I put Gn equal to An plus B is one of the simplest solution that I get to hold this equation. Now, simplifying it more, here the only constant is that you could not have A equal to 0, because otherwise then Gn is a constant and you will get A2 into constant into r to the power, which is linearly dependent here. I need two solutions because it has two roots, but my problem is two roots are same, hence I need to make them linearly independent. So to make them independent, the minimum possible or the simplest possibility is Gn equal to n, where A equal to 1, B equal to 0. So that's why I put here A2 into n into r to the power n as my solution. So this is my exact solution finally. Now when we try to put and eliminate the constants with d0 and d1 as d0 and d1, we get this d0 is equal to a1, because your n equal to 0 gives just only a1 here. And your n equal to 1 gives this form, where from you can simplify a2, and finally this is your unique solution. But however, you can see that if there are second order equation, this is we are trying to see there are second order. So let's say if the order are more and if we have equal roots, so when you take a2 into n into r to the power n as one of the answer, if you have multiple equal roots and if this order is more, if the characteristic equation has k order, then the next equal root you cannot again take a2 into n into r to the power n, because that will restrict you. Any order of n here in terms of Gn will restrict you to make it linearly independent. So remember, you have to take solutions as the same number of roots, but if they are equal, then you have to make it linearly independent. So what we do is that for k equal roots, we just increase the exponent of k by 1 and make this as my solution. So the first root is a1 r to the power n, the second root is a2 r to n r to the power n, the third root is a2 square n r to the, into r to the power n. That's why for k roots your Tn will be all of this. So for second order, we have restricted it till here. For kth order, we need to take this form. So all of them are independent solutions, and then we can form the Tn like that. Let us end up with an example where we see two roots. Same determinant example if we just give the value 2, 1 followed by 1 to 1, 1 to 1, 1 to 1 and so on, ending with 1, 2. What is your D1? D1 is just 2. What is your D2? D2 is 2, 1 and 1, 2. So, 2 into 2 minus 1 into 1, it is 3. What is your D3? If you solve this one, you will get 4. So, this way, if you try to again expand this determinant 2 into dn minus 1, because 2 into the form of dn minus 1 eliminating first row and first column stays the same. Minus 1 into dn minus 2 again, if you see, this stays the same. So, as per our previous way of computing the recurrence, we get dn equal to 2dn minus 1 minus dn minus 2 with these base conditions. So, this is x square minus 2x plus 2 equal to 0 gives me x minus 1 whole square equal to 0. That means 2 equal roots, both are 1. Since both are 1, I have to take one as a1 1 to the power n a solution and second as a2 n 1 to the power n as a solution. So, this is the final solution, and with d1 equal to 2 and d2 equal to 3, I just get the answer as both of them as 1. Interestingly, both of them 1 means my determinant is just 1 plus n, is it? See, d1 equal to 2, d2 equal to 3, d3 equal to 4, d4 will be equal to 5. Just verify yourself. So, with this, we come to a position where we could say that we have also learned not only the first order to solve the first order recurrence, but also the second order homogeneous linear recurrence where we could formulate characteristics equations. And we have seen in this lecture that how we could solve them if we have equal roots, if we have distinct real roots, if we have distinct complex conjugate pair roots. The way to determine the constants is the same, just by using or replacing with the base conditions and try to figure out. But the way to go with formulating the solution differs when you have non-equal roots versus equal roots. In case of equal roots, we have seen that we need to raise n to the power to form different linearly independent solution terms for Tn. So, let us conclude today's lecture with this note of solving the second order recurrence relations which are linear and with non-constant coefficient. In the next lecture, we will try to see that how more complex equations we can form and we can solve it. Thank you.